All right, so this video is meant to help you guys basically get the review that you would have had, or at least hear my side of why these problems were important and what you're going to see again when it comes time to taking the exam on Wednesday and Thursday when we return to school. So what I wanted to start with was the review guide, right? This is straight from the Unit 4 packet. A lot of this material is old. It is from our last unit, from Unit 3, because remember, our projectile problems, horizontally launched projectiles or vertically launched projectiles, or projectiles at angles, contain components of drop problems and vertically launched projectiles. So because those concepts, those patterns for solving a problem are going to carry over from one unit to the other, I thought this would be an important thing to go over and talk about a little bit. But also, this will be kind of quick because a lot of this we've already seen and already had. So remember, these are the 5 things that we will always know about vertically launched projectiles. This would help us in a projectile at angles sort of problem because these are the exact same things that you would normally see. Number 1, obviously, is going to be provided at the top, I think on this exam I put it at the bottom of every page, but it's still there. The rest of these hold true though, right? Your vertical velocity at the top, your time up and time down, initial velocity in the y direction and final velocity in the y direction, all of those things that we've already talked about being the same or being 0 are still going to be the same and still be 0. Number 2, this is a vertically launched projectile problem. This is one of the ways you could approach these even when you're doing your projectiles at angles. Just remember that if you set one of your velocities to be 0, like here we set the velocity at the top as 0, and then because we set the velocity at the top at 0 and we plugged it in for our final speed, this is not the whole trip. All right, this isn't measuring the amount of time that it took for the entire rocket to go up and back down, for the entire trajectory to have occurred. This is literally just the amount of time to go from the beginning to its highest point, halfway. So if they had followed up with number 2 or phrased it in a different way and asked you what is the total time the rocket would have been in the air, you would have had to double it here. Or if they had asked you what the total time in the air was, I would have personally just set -40 as my final velocity, right? Because the velocity up and the velocity back down are the same. That's number 3 from the first question on this review guide. I would have done it that way. But if you use 0 for any of your velocities for a throw-up problem, that represents half your time or half your distance, always. We've got ourselves a drop problem. Don't forget that your distances you fall need to be negative because gravity is also negative, right? -10 meters per second squared is always going to be gravity. And yeah, you absolutely do wind up with 1 second in the air. If you go back to assignment 2 in this exact same packet, you will have seen that after 1 second of free fall, we fell a distance of 5 meters. We had calculated it going the other way at the beginning of the unit when we started all of this. And then this kind of letter B should have been relatively conceptual once you realize how long it was falling for. I could have gone back to what was provided up here with the 5 meters and used VF squared equals VI squared plus 2AD, and I would have got the exact same value, all right? Twice of that 5. And move it on over, take the square root, you would have got 10. All right, it would have worked out to be 100. Square root of 100 is -10. Again, our juggler stuff, if they give you the total time in the air, I would encourage you to go ahead and split that apart. Kind of like if you're solving a puzzle, you automatically set the corner and side pieces apart. It's just a good, first step to try and organize stuff for you. If they give you the total time in the air, I would split it in half, right? Now, if you're looking for the total distance that it covers, or if you're looking for one of the velocities, then you might not need to cut the time in half, but I would encourage you to do so in case you have to, set your initial velocity at 0, basically, and use this particular equation, because this equation only works if you start at 0 and treat it as a drop problem from the top on the way down, which is why I only used half of the time. There won't be problems on the exam set up like number 4 in terms of A, B, C, and D. I would just give it to you as a one-shot. Here's the question. What is its speed coming back down? Especially things like C and D. There won't be questions like that, but you will need to apply those in order to get the correct answer. All right, maybe it's, hey, it's moving up at positive 13 meters per second, and then you would have to know that it's negative 13 to get your total time in the air or something like that. And then direction, obviously, is always going to be a test question. That's what those vectors mean, right? Negatives in physics imply direction or that you're slowing down. That's really it. Number 5 was a question about gravity. Again, I was given total time in the air. This is a good habit to get into. I did do this in order to get that initial velocity, because if I don't know the initial or final speed, then I've got 2 unknowns in one equation, and it's easier to just set one of them at 0. There aren't going to be too many trig problems on this exam, so don't panic too much. There will be one on the written portion, and then there will be one on the multiple choice. So at the end of the exam, out of the 34 points that the whole exam is worth, I think it accounts for 3 of your 34 total points. So it's not the end of the world, but trig was a requirement for being here, right? It is something that we're going to need to know. So we've practiced it a lot so far this year. It's not, the super in-depth stuff that you were going to need. If you're solving for the adjacent side, usually all we've had to do is multiply both sides by that hypotenuse in order to get it. But in this case, we were solving for the hypotenuse, and the hypotenuse started in the denominator. You cannot solve for a variable in the denominator. You got to get it out of that denominator. So you would multiply both sides by h, again, just like you always did. Then you would divide both sides by the cosine of theta. Remember, the theta is just a variable. It's just your unknown angle. Doesn't have to be anything super scary or complicated. It is where I put my 32 degrees, and that is it. This was measured from the floor, this 32-degree angle, so be careful with that. It's a lot of you guys who were asking me questions about this. We're just arbitrarily placing that 32 degrees at any of the angles that were there, but it is the angle it makes with the floor, so it goes on the bottom. And then from there, plug in your adjacent side and your angle. That's all it needs to be. The one that will be more similar to what you're going to see on the test is 8A. And it's really not going to matter which way you put them in order, the vectors. I like to add them based on what was actually given to me. So as I read this, like you would read any sort of story or book, the 3 meters per second to the east is the first piece of information I get, so it's the first vector I draw. And then from the tip of that first vector, I begin the tail of the next vector, and that was 5 meters per second south. And that's how I was able to get that. And the angle that you're always measuring is always going to be that angle from the beginning. Now, the thing I did do on this to try and help you guys out with it is I tried to, and the answer choices, only give you one of those 2 angles, right? I don't give you both complementary pairs of angles, the 2 that would have added up with 90 to give you the 180. I don't give you both of those as an answer choice, so it's only one of them. So as long as you've got both of the sides that are given as the legs of that triangle, you'll either get the correct value if you put them in the same order I did, or you'll get the complement to it, and none of the other answer choices will be there. So I'm trying to make it easy to identify. It's not meant to be that much more complicated. There won't be anything like letter C, so you don't need to worry about that one too much. Number 9, this is where we first start getting to our new stuff, our horizontally launched projectile problems. Notice that you have a vertical distance that was provided. You have a horizontal velocity that was provided, and that's always going to be the 2 bits of information that you're going to be given. So step 1 is just your vertical information, just like we did on the quiz, just like we did on, I think at this point for horizontally launched projectile problems, we've done 15 examples. I went back through all of the unit material that we've done and problems that I've done with you. It's about at least 12, I think is what I counted. And if you include the review guide, it's a total of 15. So step number 1, drop problem. Gravity determines how long that object is able to remain airborne, and in the amount of time that that object allowed, or gravity allowed that object to be airborne, it's able to travel 62 meters in that amount of time. And that's those are your 2 steps, right? We've got a drop problem, which is why I did some drop problem stuff early on in the review guide, followed by d equals vt in the horizontal direction, and that is it. You do not need to do the data table. I took the data table off of the exam. This was another way of solving these problems. It was really good, and I liked it just to re-emphasize gravity doesn't change, and because there's no horizontal acceleration, your horizontal speed doesn't change. And so I liked that aspect of it. But in terms of solving for a variable or a value, it's always just easiest to use the equations, just like we literally were just doing. And so that's one of the things I took off. Historically, not too many students really ever made the data tables and filled them in. I want to say like 5 students out of my decade of teaching have actually used that. So again, 11 and 12, we have more horizontally launched projectile problems. I want you to notice it does not matter what distance or what speed it is we're including. You never use, like in 12, 45 and 4,000 together. You never use 1.75 and 3 together. They are in different directions, and that y direction is independent from the x direction. Gravity only works in the vertical direction, and gravity is what determines how long it will go. So again, we've got step number 1, drop problem, how long is it in the air? Step number 2, how far can it go in that time? Step number 1, how long does gravity let it be in the air? Step number 2, how far can it go in that amount of time? That's all this ever is. Projectiles at angles, same idea. The only difference is that we're given a velocity that goes off at some angle. And I'm always, on the exam, because we had to shorten this part of the unit, I am always going to give you the hypotenuse and the angle. Always, 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 always. So it is up to you to find the 2 components to it. Now remember, just use the equations that I gave you, right? They should be on the board, or they were on the board multiple times, multiple different ways, and they should be all over your notes, right? We did this in assignment 6. I provided the evidence for you for how you get Vy and Vx, right? So our initial velocity in the y direction is your hypotenuse multiplied by the sine of the angle. And then in the x direction, it is your hypotenuse multiplied by the cosine of the angle. Please, 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 please make sure you're in degrees. Do not be in radians when you do this. It will not be correct. From there, it's actually the exact same process as our horizontally launched projectile problems, right? We had to figure out how long gravity allowed this to be airborne. Now we're still doing the same thing. We are figuring out how long gravity lets it be airborne. The only difference is that there is a non-zero vertical speed, right? It's a throw-up problem instead of a drop problem, but we're still finding how long gravity lets it be airborne. I think using positive 35 and negative 35 is the easiest way to do this. This represents the whole trip. If you wanted to plug in 0 for your final speed, you could have, and you would have got a time that was half as long because that only represents half of the trip. The first half of the trip right there, right? You still have to take into account the fact that it's able to turn around and come back down, and its time up and time down are the same, so you would have had to double it. Again, once you know how long it is airborne, you are then strictly finding how far it can go in that amount of time. That is it. Notice, once I calculated or resolved my vector, once I had letter A completed and done, I did not use 45 meters per second again. You should not. Once you resolve that vector, you're just using the vertical and horizontal components of that 45 at 52 degrees. Number 14 isn't one you had to do. This was the other half of the second half of the unit, right? I guess you could say the last quarter of the unit, where we would have done these projectile at angle problems in a different order. We would have played with the concepts a little bit more. You would have worked backwards to be able to find what the launch speed and launch angles were. That's not going to be in the exam. I took that off, so don't worry about it. In number 15, this one conceptually is important, but this is what your gizmo should show you and what number 16 shows you as well. So for number 16, just like I had talked about in class, we're going to use the 33.81 that you should have found in number 14. And you're just going to use it at various angles. So you'll see number 1, or this first one, at 82 degrees. I did all of the work for all of the steps, right? Step number 1, I resolved my vector. It was hypotenuse multiplied by the sine of the angle to get the y direction, and then hypotenuse multiplied by the cosine of the angle to get the x direction. I used the y direction to figure out how long it was in the air for, and then I used the x direction to figure out how far it can go in that amount of time. I repeated the same steps in every single one of them down below, but I changed the angle. And the point of this, a lot like the gizmo, was literally just to see which angle would provide you with the greatest range, the greatest horizontal distance that this object had traveled. And you'll notice that as the angle gets lower and lower and closer to 45, your range increases, and once you go beyond 45 degrees, your range begins to decrease again. The optimum angle, in order to launch a projectile and get the maximum amount of range out of it. Now we're ignoring things like air resistance and a lot of your new, I don't know, like tank and artillery shells can rotate and do some weird aerodynamic stuff. So we're ignoring all of that, but for pure projectiles, 45 degrees is going to be the best. That is going to be a test question for sure. So you've got plenty of projectile at angle problems, right? One of the best study tips I can give you guys is to put everything away, print out a blank copy of this review guide or any of the other worksheets that you struggled with and treat it like the exam. See what you can do. That would be my number one tip. I wish I wasn't 22 years old and taking the hardest science class of my life when I figured that out. But there are also other things that I provide for you guys that should be able to help. So if you go into the Files tab, Class Materials, Semester 1, Unit 4, this is where everything is. There's our gizmo that we should be working on, right? That's the one you're going to get that 45 degrees with. But here's the packet, right? Give the packet a shot. On the cover page, don't forget to check this out. A lot of us on the exams are getting things wrong that were addressed on the cover page. Here's our calendar and key equations, and then here's my list of common mistakes. Right? Check out that list of common mistakes because they are going to be things that trip people up. Here are the steps to solving all of your projectile problems. It's all there. Please, please, please use it. The other thing that is there, which is not required, but it is somewhat beneficial, is the supplemental packet. Right? The supplemental packet contains a boatload of projectile problems, projectiles at angles, conceptual problems, 25 multiple choice questions with content very, very, very similar to what you're going to see on the exam. All the answers are provided. If you get stumped on one and you can't figure it out, just send me a photo of it because I don't have this supplemental packet memorized, but we can work through it together. We can talk about it, and that's a really, really, really good study tip that I wish more people would take me up on. Remember, too, that there are also the old videos that I've made so far, right? Obviously, there was the calendar updates for what is due when. I would encourage you to check that out, but here's my projectiles at angles video that I posted not too long ago. Here's a walkthrough of assignment 4 and assignment 5, and then here are the intro notes for horizontally launched projectiles. So they're all there. Please check them out. If you've got questions, concerns, anything like that, let me know, and I would be more than happy to help you out. But that was about it. Shoot me an email if you've got questions, please.